So welcome back, everybody. And the topic today is to try to wrap up this discussion about the bootstrap method and the blocking method and point to what we need to program. And I will also say something about this one body densities, which is a technicality, and I will just put that on the whiteboard. So I'm going to jump a little bit between the slides, so the Jupyter notebook from last week and this week, and jump into the whiteboard as well, and try to expose to you this blocking method, which is the one which you normally would use when you have millions and millions of Monte Carlo samples. So if you're having just few results, like you would have from some intensive calculation with, let's say, thousands to 10,000 results, and you assume that they're roughly independent, then the bootstrap method is normally the one which is chosen. But we will stay with the blocking method, and I will try to explain to you, based on that definition we had last week, on the covariance and these quantities. So I'm going to remind you about the equations which we derived last week. And then I will jump a little bit back and forth between some demonstrations. In the Jupyter notebook for this week, you will also find a code which calculates the correlation or the covariance matrix, the autocorrelation function, which we roughly defined last week, which we need to bring back. It calculates the standard deviation with bootstrap and blocking on a random number generator. And these are the numbers which we will then just play around with to demonstrate the different methods. So you will find that at the end of the Jupyter notebook. But we need to revisit some of the formalism which we discussed, and then I will try to give you the basic ideas of the blocking method and why it works. Okay, so the main idea behind the resampling methods is that our simulations are actually numerical experiments, and this is actually the case for Monte Carlo methods. You can analyze the results with the tools from statistics as you would analyze experimental data. And then what we want. And as I said last week, you may ask, why do we stress so much about this tiny result which we're looking after, which is the standard deviation? Now, the main reason is that when we do implement a stochastic method like Monte Carlo methods, there are statistical errors. So we will have a sample of data, and that are our measurements, that sample of data. And when you calculate the mean value, since you don't know the probability distribution behind the stochastic variables, then your mean value, your variance, etc., are approximations to the true value. So if somebody gave you the true probability distribution, and if you could calculate the expectation values, then you would have the exact values. Unfortunately, we don't have this quantity. So our distribution is obviously the Monte Carlo wave function, the optimized wave function, but we will never be able to calculate the expectation values exactly with that. So that means that we have statistical errors, and these can be treated. So the more difficult ones, like the systematic errors, these are things which go back to the basic assumptions about the science we're doing, in our case the Hamiltonian which we're using, and these are much more difficult to evaluate. And that's why statistical errors, these are things which we can do, and then we should do it. Because when you run a calculation like a Monte Carlo calculation, if you, as I said last time, if you don't provide a standard deviation on your results, nobody will believe your numbers, period. And the same applies if you run an experiment. Okay? So let's bring back the whiteboard and say a little bit about the things which we derived last week. You will also find everything in the Jupyter notebook from last week and also this week. But let's slowly remind ourselves about where we landed last week. And I have to make sure I have the right notes. Yeah, here we are. Good. So the thing which we did was what is often called a naive estimate of the mean value. So what we calculated was the mean value, and this is normally called the mean or the sample value because we have a sample of measurements. And since we are dealing with a discrete set of events, then this quantity which we labeled with X or mu, so different names, sometimes you put an X, a subscript on it, and this is given by 1 over n, the number of measurements which we have, and I equal 1 up to the number of measurements, and then the observations. Then the variance of this quantity, the variance of X, of this data set, is then typically written like var X. And what we saw then is actually that we have this quantity sigma squared divided by the number of measurements. And this sigma squared is nothing but the variance. And now I have to of a given measurement, which I write like an X. And these are the X's which you have here. So when we now repeat this X bar here, what we are doing then is that we are setting up a whole series of experiments. And what we found then last week, and let me just bring this up, is that the variance of all these measurements, so this is something which we label with a sigma squared n. This is this quantity here. Since the data are not independent of each other, this is given by the following function. So we have 1 divided by n squared, and then we have a sum over I equal 1 up to n, a sum over j equal 1 up to n, and this is given by the covariance of an event xi minus the mean value, and now we are assuming that the mean value is the same for all the observations. And these quantities, now let me write it, let me write it fully out here. So let me just write it like an x of I minus this mu, mean value, of x of j minus mu. And this quantity which you see here is normally called the covariance between xi and xj. Now, the covariance between these two quantities, this covariance of xi, xj, is normally different from 0 when xi and xj are not independent. If these are independent and identically distributed variables, then the covariance is equal to 0. Now we have to be a little bit careful because this sum here can actually be written out in terms of a single sum. If we take the diagonal elements of n squared, the sum over I, 1 up to n, and this is xi minus mu squared. And this is just a single variance. This quantity which we have here was the same as the variance of a single experiment divided by n. So where the variance of a single experiment is actually given by this quantity here divided by n. And then we have a sigma squared divided by n. And if you think back to the theorem which we derived last week, the central limit theorem, if the results are independent and identically distributed, then the variance of n such experiments is actually given by the single variance of one experiment divided by the number of experiments. So this is the result which you see here. This one is the one which you get from the central limit theorem, which we proved last week. But if you don't have independent variables, then you need to pay attention to the covariance as well. So we get an additional term. Now, the covariance is symmetric, which means that you can then rewrite the sum, and you would rewrite it like 2 divided by n, and there is a double sum of k and l, and then you have xk minus mu times xl minus mu. And that last term is the covariance, which then represents the non-diagonal elements. Now, this quantity which you see here is normally also called the covariance matrix. You can define a so-called covariance matrix. But let's now take and rewrite the equation. So what you can do now, if you look at this expression, we can then do a plain rewrite. So it's often this term, if we just rewrite it, is given by 1 over n squared. And then you have a sum over I of 1 up to n. And then j equal 1 up to n. And you have the covariance of xi, xj. And it's often written in terms of the elements of the covariance matrix. So you will often see this one rewritten as a sigma ij. And this sigma ij, the thing which we did last time was actually to make an assumption that we could rewrite. So if we now look at this covariance term which we had here, this one, what we did was to redefine it, and we simply assume now that we could assume that there is a distance between a measurement k and a measurement l. So the thing we did last week was actually to rewrite the covariance in terms of a function, and this is more or less where we ended last week, the sigma squared divided by n plus 2 divided by n, and I just put dots here. So this term is something where we introduced a function which we call for f of d. And this function f of d was defined as 1 divided by n minus d. And then we have a sum which goes from k equal 1 up to n minus d. And this was given by x of k minus mu here, multiplied with x of k plus d minus mu. So what we did was simply to define this L as k plus d. So the assumption which we are going to make is that this d is now going to be, because there is a symmetry in the covariance, that this is given by L minus k. Now, what we are hoping for then is that when d reaches a certain value in this formula here, when it reaches a certain value, the hope then is that these events which we have will be uncorrelated. Now, this function which you see here, if you now replace d with a variable called t, and you can interpret that as time. So you could think that at the time k, you make a measurement, and then you move at the time L, which is then the difference between k with an entity d here. You could then think of this as measurements at different time steps. So this leads to the definition of something which in statistics is called the autocorrelation function. And you can actually show, and I will show you that because we have it in these slides from last week. You can actually show that this term, when d becomes large, typically goes to 0. So this is an assumption which we are making about the data which we have. So you can then think of you having a set of measurements. So if you look at a one-dimensional axis here, so you have d, which you could interpret as time. So you make a measurement at the time k, and then you make a measurement at the time L, and then you're asking yourself, how big is this distance between these measurements before you can start interpreting the observations as independent of each other. And if they are independent of each other, then the covariance which you have here, this term which we have a plug, or this term here, goes to 0. And that means that your variance for the whole set of experiments is actually approaching the result which you have from the central limit theorem. So the result which you see here is simply from the central limit theorem, assuming that the events here are independent. But in our case, since we produce correlations in the data sets and we have a random number generator which depends on a deterministic algorithm, it means that the events will have some degrees of correlations. So our events are not stochastically independent of each other. So the question is, how long do we need to simulate now, which means this quantity d, before we can let this term here go to 0? And how fast that goes to 0 is important for the blocking method. So let me try to rewrite slightly these equations which we have here. So when we have this term f of d, what we can do is to rewrite our total variance. And what you typically would do is also to define a function, a correlation function. This is actually the basis for the autocorrelation function, where I take this function f of d and divide it by the variance of a single measurement. And what we saw last week is that when this d is equal to 0, then this quantity f0 is the same as the variance. So that means that this function has a peak value equal to 1. But what we would like to, if this f of d goes to 0 quickly, is clearly that this function kappa is something we would like to go to 0 as soon as possible. And the final equation which we derived last week is the one where we have the variance for all the measurements which we are running, which is given by the variance of a single measurement plus 2 over n. And this has a sum over this function d equal 1 up to n minus 1 of the function f of d. And we can rewrite that one in terms of this function kappa. And you can see that this is something we can rewrite like 1 plus 2. And then we have a d equal 1 up to n minus 1. And then we have this function kappa of d multiplied with sigma squared divided by n. Now, the things which we have in parentheses here is something which also defines an autocorrelation time. And this quantity is defined as and I'm going to define that one as a tau. And that is defined as the terms which we have inside the parentheses here. So that means that what I can do then is to redefine my variance in terms of this term here, of 1 plus 2 times the sum over d equal 1 up to n minus 1 of this kappa of d. And that gives me a total variance, sigma squared, which is the same as this tau divided by n times sigma squared. Now, if you want to, you can change this d into a time. Now, what this gives us is actually an effective time. So you can actually rewrite this in terms of this time which you see here. So the interpretation which we have is that we have a tau represents the number of measurements we needed in order to establish when we can consider an experiment or a numerical experiment. So when I say experiment, in our case, it's a numerical experiment. We can consider an experiment to consist of independent variables or of independent quantities, statistically independent events. So you can actually show that if you now want to interpret, so what you could do is actually to interpret this D as some kind of time, because the way you can think of it is that you make a measurement at a time K, and you're actually doing that when you're running your Monte Carlo calculation. You could think that at every Monte Carlo step you do, you could think of that as a time step. So you run an experiment, you have your system in a specific position, then you go to the next time step, etc., etc. And what you would like then to see is that these events actually become uncorrelated. So typically when you look at this term here, we can now rewrite it a little bit. So let's do that, because then what we want to do now is to bring this in contact with the idea of the blocking method. So what I'm going to do now is simply to assume that this covariance of two events, xi and xj, that depends only on the distance between the two experiments. And this is essentially what we've been doing when we rewrote this function f of d, and then this correlation function kappa of d. So it depends only on the distance which is I minus j. So we have the covariance there for these two events. So that means that this element which we wrote as a sigma ij, the covariance, is then a function which now is going to depend on I minus j. And what I'm going to do now is simply to write this as a function c, just for shortening the notation here, right? So this is going to be a function which depends only on this distance. And what we have seen then is that the variance, which we have set up, the variance for all the experiments, sigma of n, is 1 over n squared. And we have a double sum over I and j. And we can rewrite that one in terms of this distance I minus j. And what we could do, and this is something which I'm setting up now in order to get in touch with the article of Hjorth-Jensen and Petersen, which were the people who introduced the blocking method first. So in the article there, which you have a reference to in Hjorth-Jensen and Petersen, and these were the people who introduced the blocking method first. What they do then is to introduce a variable which they simply call for t. So you can think of that as a time between measurements I and j. So what we have then, if you think of this term here, when you take for t equals 0, what we get then is just a variance. Then this sigma squared divided by n is actually equal to, the sigma of n is equal to sigma squared divided by n. So in total then, when you look at this sum, there's a 1 over n squared. So for t equals 0, there are actually n terms. So we have then n terms. If I take t larger than 1, what we have then there are in total, and keep in mind that the covariance is symmetric. So if I have a covariance of events 1 and 2, that is equal to 2 and 1. So the covariance is by definition a symmetric quantity. It's also a quantity, if you think of this as a matrix, this sigma, this matrix here is actually positive semi-definite. So which means that all the eigenvalues are larger or equal than 0, because the variance when you diagonalize the covariance matrix, if you diagonalize this one, that gives you the variance of the system, the diagonal elements. So the variance is always larger or equal than 0. It's a positive quantity. So if I do that, since the matrix is symmetric, if you do the counting then there are 2 times n, no, sorry. There will be 2 times n minus t terms. It's actually not so difficult to see that. Since both, if you look at the quantities I and j, so the matrix is symmetric, and j and I contribute and are the same. So when I look at the double sum then. So what I can do then, if I now look at this quantity, so I decided that c of I minus j, instead of summing over I and j, is something which I'm going to call c of t. So just to bring back the notation here, I shortened, instead of writing sigma j or covariance, I just write this as a c of I minus j, okay? So that is just a shorthand which I've introduced. And then, since I'm using that notation, I can actually rewrite this quantity, sigma squared, as 1 divided by n squared. And then I have n times c of 0. So this quantity here, which I have the c of 0, is nothing but the variance of a single measurement. Plus, and now I have a term which goes like 2. And then I'm summing, instead of I and j, I have a sum over t, and this goes up to n minus 1. And then I have n minus t multiplied with this c of t. So what Flyberg and Petersen did was to take that equation we derived last week and rewrite it, assuming that the covariance depends only on the distance between the two measurements. So with that rewrite, you can keep going a little bit here, and you can then find, if we now remember this function, which we define as a k, kappa, and instead of having d, we are going to let this to be a function of t, because t is now replacing this variable d, which was the distance between two measurements. And this is the same as this function now, which would be c of t divided by c0. And c of t is the covariance for two events. So this would be c of t divided by sigma squared. So this is just the same as we had before. This is the normally called the autocorrelation function. And since we have time, you will often see this being called in the literature for the time autocorrelation function. The way you have to think of it is as the distance between two experiments, and that this distance, in our case, can be interpreted as a time, because you make a measurement at different times. So when you then rewrite everything, you can then rewrite sigma n with sigma squared divided by n, as we had before, or 1 plus 2 divided by n. And then we have this variable where we have now we are summing over t up to n minus 1. And then we have an n minus t multiplied with this function kappa, the correlation function. And you can rewrite it further. So we can rewrite it like a sigma squared divided by n, and then we would have a 1 plus 2, and then we have an t equal 1 up to n minus 1, or 1 minus t divided by n, multiplied with this function kappa of t. So this is just a plain rewrite. In principle, what we want is that n goes to infinity. So we would like to have an infinity of measurement. And this is what the blocking method deals with, is actually us letting this n become larger and larger. So we are going to make an assumption, and you will see that the autocorrelation function, which we have put in here, is actually a function which goes to 0. And you will see that in the simulations which we are going to run when we set up the autocorrelation function. So that means that this function here, if we now take a sum from t equal 1 and let it go to infinity, and then we look at the absolute value of this function, k of t, what you will see is typically, for most cases, that this is not a term which diverges. Actually, the most standard case which you will see as a function of t here, and we are going to see that in the codes which we have in the Jupyter notebook, is that when you take t equal to 0, then this function kappa is equal to 1. So you have 1 here, and then what you would see then is that when you get closer and closer to larger values, is that this function drops to 0. Actually, it will oscillate around here, and then after some time, it just vanishes. So it means that there is some kind of ideal time when the correlations disappear. And then you can start thinking of your measurement made here and the measurement which you make here as statistically independent measurements. So the blocking method is a method which actually exploits this feature, this property, and it uses that one to evaluate the standard deviation without having to calculate the covariance. So that's the whole trick. And so let's see what we can do now. So if you look at that expression which we had here, if you now assume that you let n become very large. So if n is very large, what happens then is that this quantity here goes to 1. We can approximate it with 1. So if we now assume that this is the case, that the autocorrelation function disappears, then for large n, what we have then is that this 1 minus t divided by n, this becomes closer and closer to 1. So that means that we can approximate these measurements, sigma squared n. We can approximate that one with sigma squared divided by n, of 1 plus 2, and then we have a sum from t equal 1. And in principle, we could put infinity here, but we are going to put n minus 1, and then we have this correlation function kappa of t here. So this is the equation which Blyberg and Peterson used when they started with setting up the blocking method. So let's see what the blocking method is actually doing for us. So this, what we have done here is nothing but a simple rewrite of the variance for n measurements. So if we believe in the central limit theorem, we would obviously only have this term. Now, since we know that the variables are not independent, it means that what we need to spend some time on is actually to evaluate that. So this is a positive quantity. This is obviously a positive quantity. So if we only take this quantity into account, we will get an over-optimistic evaluation of the standard deviation. And you will see that when you run typically the standard bootstrap method, which assumes independent variables, then this quantity here is the one which you will get for the standard deviation typically. Okay, so you might ask, I mean, why all these efforts, right? Why do we just don't calculate that one for the single experiment? The reason is simply because we don't know how big this one is. So that means that we could actually get a standard deviation which is too small. So in Monte Carlo calculations, one of the big issues is you providing a reliable estimate of the standard deviation, period. And that's why we do all this kind of efforts. So it sounds like an overkill. We are mounting a big machinery to simply evaluate a small number because the standard deviation is normally pretty small. Okay, so the blocking method is actually a way to avoid to estimate the autocorrelation function. Because keep in mind that if you now look at the original expression which we had, the original expression, if you look at the expression for the autocorrelation function, this involves you evaluating a double sum. So if you have 1 billion Monte Carlo cycles here, it means that you have to do 1 billion square. You will see that even if you have, and in the examples you find in the Jupyter notebook this week, what you will see there is that we have an example where these x's are not the x's from the Monte Carlo calculation you're going to run, but they're just random numbers. So actually this function, as I mentioned last week, is normally used to estimate whether a random number generator is a good one or bad one. Because a random number generator is a generator where you want to have stochastic independent variables. So that means that you want to see this one go to 0 as fast as possible. And even if you take a random number generator and you take 10,000 samples, it means that if you want to evaluate this expression, you have to do 10 to the 4 squared. And you will see that immediately when you run the codes, it's going to be slower and slower for more data points you have. So if you calculate this one with 1,000 data points, it's going to be pretty fast because you would have 1 million evaluation. But as soon as you go to 10 to the 4 or 10 to the 5, then you have 10 to the 5, you would have 10 to the 10 evaluations. So that means 10 billion evaluations. And that's going to be slow. You could try that with the codes which you have. There is a code in today's Jupyter notebook where you can evaluate the autocorrelation function and the covariance by using the standard direct formula. And you will see that when you increase the number of points, it's going to be slower and slower and slower. So the whole thing with the blocking method is actually to exploit this property of the autocorrelation function, which we have rewritten here, this one, and then exploit neighboring samples where we split them into blocks. And each blocking level is going to reduce the correlations. So let's just set up some of the basic ingredients of the blocking methods. So the idea behind blocking. So we don't evaluate the covariance of xi, xj. But what we do is that we combine neighboring samples into blocks. And each blocks, or each blocking level, as we call them, each blocking level is then meant to reduce the correlation between the neighboring blocks. So if these blocks are large enough, then what we are going to have is independent samples. That's the whole idea behind the method. So what you would do then is to start with a data set, and then you have a blocking transformation. So that will keep, I mean, your total variance is going to be preserved because you're just changing the way you organize the data. So the mean values have to be the same, and the total variance has to be the same. But what changes, so what you would do now is you would start with a data set. So where we have some x of I, so this is our full data set. And then I runs from 1, 2, up to the total number of data. So this is data set 0. Then you can define a blocking transformation. Define the blocking transformation as follows. Mention as. So I have a new data set, and I have split my data set into blocks of 2 all the time. So this is given by 1/2, and then I have x of 2i minus 1 of the previous block, k, plus x2 of I of k. So what I'm doing, and you probably saw in the code which I presented last week, that we chose the number of Monte Carlo cycles to be 2 to the power of Monte Carlo cycles of n. And the reason for that is simply because then it's very easy to split your data in blocks by dividing by 2 all the time. So what you're doing then is you take this data set here, and then you just split it in 2 blocks. That would be your xi of 1. And then you would have the 1/2 and the other half of your data. So the properties of the method then is what you get then, the properties here, and what you will see. And after the break, we are going to look at the derivation of the method and the algorithm for the method. So the properties is that the number of halves of samples halves each iteration. And the correlation decrease with blocking level. So after k transformations, what you have, after k transformations of this type, what you have is that the number of data which you have in each block is then given by the original n divided by 2 to the power of k. And what you will see is that for each of these cases, so you would compute, and let's do this before we take a break. Let's just set up the basic ingredients. So you would compute the mean value for a specific block, which is given by 1 divided by n, or rather this nk, which we put up here, sorry, of nk. And this goes over I equal 1 up to nk. And I have my x of I, this block k. I estimate the variance. And this variance of sigma k squared is going to be given by 1 over nk minus 1. And then I equal 1 up to nk of this xi, k, the data points we have in that block, minus this number x of k. So that means that the error estimate which you make for that estimate. And after the break, we are going to show that this is the case. So we have an error estimate is going to be given by a sigma k squared, which is then going to be given the final error estimate. Wait, this is Now I should change the notation here. So this is for the specific block. This is given by S of K. So the total error estimate after we've calculated this block is going to approach this X of K divided by NK. And what we will show is that this sigma K squared goes actually towards this value which we want to have, sigma squared divided by N. This is what we are going to show after the break. So instead of us calculating the autocorrelation function or the covariance, we actually simply performing the standard single sum. So instead of you evaluating, let's say 10 billions or 1 billion squared, you're just doing 1 billion evaluations. And that is cheaper than doing 1 billion squared. So the whole thing is that for each of these blocks, you simply evaluate this quantity, and you can then show that this quantity, which you then evaluate, this error estimate, when K becomes large, it actually approaches the true variance, which is then given by the equation which we put up here. So the way we are doing, what we are doing with the blocking transformation is that we are trying to approximate this quantity here by just evaluating the variance of the blocks. Now, what you can show with the blocking method is also that the mean values is preserved, and also the total variance has to be preserved. So these quantities cannot change because you're just making a transformation of your data sets. But what you're doing, instead of evaluating this quantity here, which is extremely time consuming, is to actually evaluate the variance of the single blocks. And that saves you a lot of CPU cycles. And you can show that this converges. So it converges to a fixed point, which is actually the final variance. So after the break, we are going to look at how this links with that expression with the autocorrelation function. And we're also going to set the algorithm step by step. And then we are going to also discuss briefly the bootstrap method again. And then we have essentially all the ingredients which we need. Any questions? So typically people, it depends, it will always depend on the number of particles you have. And you don't know that from the beginning. But you would typically at least need 1 million samples, typically, when you have, let's say, 10 or more particles at least.
It's just that it's treated in cycles,
yeah.
But the code is saying data. But I don't think it's possible on data in our case because the code is already quite small.
So you have to, when you run Monte Carlo calculations, you simply have to state, to be honest, and say simply, the resources I had didn't allow me to run with billions of cycles in the time I had at my disposal. Period. So when you run the calculation with 1 million samples, the error you get is the error you get. Period. And you have to cite that one. And then you simply write that I know that in an ideal world, if somebody gave me access to a supercomputer and I could run for months, I would get a better and better error, right? But it doesn't change the science. So you're just getting the science at a given level of precision. And that's what everybody does. I mean, if you run an experiment, you know that if you run an experiment at CERN, an experiment can run for half a year. And unless you can come with very strong claims that redoing the experiments can lead to a Nobel Prize, nobody will give you more beam time. So keep in mind that the electricity bill of CERN is more than the electricity bill of the whole city of Geneva. Only the electricity. And they do shut down in winter for maintenance because that's when electricity prices skyrocket. So CERN is closed experimentally in November, December, January, and February, by obvious reasons. So you just have to be honest. This is the data I have. If you run a medical survey, some of these, there was one in the UK where they mapped out heart disease in the population, and they followed 500,000 people for 30 years. There's no way you will get money to redo that. The data you have is what you have. And then you have to use the tools from statistics to analyze the data. And that's why these resampling methods come in. The discovery of Higgs was actually a statistical tour de force. Statistical tour de force. So they used really advanced statistical methods to evaluate the discovery of Higgs to 5 standard deviations. Let's take a small break and then do some 15 minutes. So the blocking transformation which we are dealing with is the one which we mentioned before the break. And this is a kind of coarse graining of the original correlated sequence. The effect is actually that you suppress short-range correlations. You can actually see that if you take some of the examples we have in the Jupyter notebook on the random number generator. And it reduces the off-diagonal structure of the covariance matrix. And at sufficiently high blocking level, the transformed covariance matrix becomes approximately equal to this variance which we extract from the single experiment. And the total variance, the one which we call sigma squared of n, is actually going then to approximate the different independent sample formula. So blocking is a practical numerical procedure for converting the full covariance structure into a reliable variance estimate. And one of the equations which we looked at, so actually here I call it for rho, but it's actually the function which I call for kappa. This is the correlation function. This is the covariance matrix. And this is the total variance. And for large n, the variance actually approximates this tau in this effective time, which we had in the lecture notes, times the variance of a single measurement. And that's normally the theoretical foundation behind the blocking analysis. So the way you would set it up, you first compute the variance estimate, sigma 0, which is the one which is the direct variance for the single data. Then you perform these blocking transformations and you recompute this variance. And you repeat until this nk, you just continue until you reach a plateau where the variance becomes stable. So what happens when you apply this method, let me just go back to the whiteboard. So what happens when you apply the blocking method is that you will see something like this. So your sigma 0, which we had in the slides there, is the same as the single experiment divided by n. And this single experiment one is the same as 1 over n, and then I simply have x of I minus the mean value squared, and then the sum over all the single experiments which we have run. So this is the value which you would start with, like this. And then you set up different blocks. So this is a function of blocks here. So that means that every time you divide it in blocks of 2. And the next time you may find something which looks like this. And the next time something like this. And you will see that in the demonstrations which we have numerically. That when you reach a plateau like this is typically when the standard deviation then reaches the limit. And you can actually show that if you have the exact expression for the standard deviation, for let's say a model like a Gaussian distribution, you should actually be able to approach if you have brought in correlations in the data set. So you can take a multivariate Gaussian distribution with a given covariance matrix. And then you know exactly what you should get. You can then show that the blocking method actually converges towards the correct variance. So ideally, if you were not to include the correlation function, the covariance, you would make a too optimistic estimate of the standard deviation. Now, one thing I wanted to say quickly, something about. So essentially what you do, you keep subdividing, and then when you plot these variances, and when it reaches a plateau, you would then say that now I've reached the stable inlet. That's the standard recipe, which was introduced by Flyvbjerg and Petersen. Now, the notebook, in the notebook which we have implemented a modification which was developed by actually, this was a former master student of mine, but basically the master thesis was, so this was a student who actually had a background in statistics and was frustrated with the proof of Flyvbjerg and Petersen and developed a more rigorous proof, and then an algorithm for actually finding that plateau in a more efficient way. And the algorithm which you have in the Jupyter notebook is actually what Marius did for his master thesis. And this is an example of where the course leads to a scientific article. It was published in a scientific journal. And it was simply because Marius was frustrated with the Flyvbjerg and Petersen proof. He didn't understand it, and then he wanted to prove it himself. So that's what we always want, the ideal behind a course, right? For progress. Okay, so I wanted just to say something quickly about the bootstrap method, and then we're going back to the codes which you have access to. And now I need to find back my, where did I do that one? Yeah, I need to do that first. Okay. I have too many windows. Here we are. Okay, so let's take the full screen view. So I wanted to say something about the bootstrap method as well. So in case you want to implement that one, and that's typically used for smaller data sets, and in particular when you have independent stochastic variables. So if you think of a summary here, the Monte Carlo samples are typically correlated. The naive variance estimates underestimate errors, and blocking reduces correlations through recursive averaging, and the variance converges to a plateau corresponding to the correct error. So it's a simple method, and it's widely used in computational physics applications. And it's for large data sets. It's typically one of the more used techniques. The idea behind the bootstrap, which we discussed a little bit last week, is actually to, we have an unknown distribution. We don't know the distribution, but we only observe the samples. And the bootstrap replaces the unknown distribution by an empirical distribution, which is then defined by a delta function. So that means that your probability is 1 over n, essentially. And that's something which we have actually done when we run the Monte Carlo calculations. So we treat the observed data set as a population, and you generate new samples by resampling with a replacement. And that produces a systematic data set from this original distribution which we have here. So you see every event has the same likelihood, 1 divided by n. That's the basic assumption. And we will typically generate a bootstrap sample, and we defined that last week as well. So we have the new sample where we draw n values from the original data. So one of the examples we saw last time was an example with integers, but now you can just set these numbers, and you see that you can actually, since you're dealing with a replacement, you can pull out the same number twice or more. So each bootstrap data set is going to mimic an independent experiment. And for each bootstrap sample, you would compute the an estimator, which could be the mean value, and you repeat this procedures b times, and then these values form the bootstrap distribution, which then approximates the sampling distribution of the estimator in the large limit of n. And you will see in the example which we have in the Jupyter notebook, where we take the random numbers. So I just take the standard random number generator, and then I calculate the autocorrelation function. I calculate the standard deviation, the mean value with the bootstrap, the blocking, etc. So you can look at those examples as a way to convince yourself that these methods are not that bad. And typically then, what we do is to the bootstrap estimate of the variance is then given by, if these are the mean values of each experiment, this is actually what we will set up. And the bootstrap standard error then becomes simply the square root of this variance. And as b goes to infinity, the estimate actually converges to the true variance if you have independent value. And if you let this be an estimator, so this could be the mean value as a typical estimate. There's something which is called a mild regularity condition from statistics, and this has actually a limiting distribution. And you can actually prove, and this was done by Efron and many others, that the theory shows that this one approximates the same limiting distribution. So this is something which we are not going to prove, we are just stating that actually, if you go more in depth, you can actually show mathematically that you are approaching the same limiting distribution. And that's the kind of theoretical justification for the bootstrap. When Efron presented it the first time, he actually just presented it in terms of the algorithm here, without a more rigorous proof. And then the proof came later. And you would then also find, I'm going to skip some of these things. I will just put up, you can take a look at it. So the applications of the bootstrap method is actually pretty widely used in quantum Monte Carlo, experimental particle physics, just to give an example, in molecular simulations, in any type of experiments. And typically you would calculate correlation functions, you would look at fitted parameters. So the estimators are the quantities which you want to estimate. For those of you who took a course on machine learning, you have encountered the bootstrap method as a way to do resampling. And if we look at the calculations which we are doing in a Monte Carlo calculations, this is the mean value which we would typically evaluate. But we also want an uncertainty for a nonlinear function, which could be an expectation value divided by another expectation value. And the analytic variance formulas, they become pretty complicated. And the bootstrap procedure, simply you resample these two quantities, you recompute the ratio, and you obtain a distribution of R. So if you look at the variance, this is not given by a ratio, but it's actually given by the expectation value squared minus the expectation value of the mean squared. So if you think of this compared with many other methods, the advantage is it works pretty easily. It's easy to implement. It provides often a full distribution. However, it's typically used for smaller data sets. It's often used for data sets of the size of 1,000 to 100,000. It has some limitations, and that it assumes independent samples. For correlated Monte Carlo data, we often combine the two or just use one of them. And the typical method, which is widely used, is blocking. That's the most used one for this type of data set. So it's a powerful method, but for the calculations which we are dealing with, where we can produce millions and millions of samples, then a blocking analysis, when it converges, it will reach a plateau. It gives a reliable estimate, and it doesn't assume that you have independent events. Yeah, but when you reach that plateau, that's typically when you can say that the blocking method has converged. And you can actually, if you take some simple examples like a multivariate Gaussian distribution, which has a covariance which is not necessarily equal to 0, you can just define that. If you use the scientific Python, the statistics package there, you can actually set up a multivariate Gaussian distribution with a non-diagonal matrix elements for the covariance. And then you will see that the blocking method actually approaches the true variance. Because then you will have correlation. And then you will see that the bootstrap method does not do that. Okay, so what I want to do now is to switch back to the Jupyter notebook and look at some of the examples which we have. You see, before the break, we actually started this job with 100,000 cycles, and it's still running. So that's an example of why you don't want to calculate the autocorrelation. And this is a small set of data. So if you were to generate 1 million data and you were to do a post-analysis where you calculate the autocorrelation function, it would take time. So don't do that. But let's, no, that was this is today. So let me just stop this one. So what you find basically here, just a repeat of what we did. And the thing I wanted to say a little bit about is, again, the codes which I presented last week. So in that code, we have a different physics case. It's 2 electrons which interact with a Coulomb interaction, but it's close to what we are dealing with. And in that case, the wave function has a single particle piece and a correlated part, which we call a Hjorth factor. And in this case, we also have the local energy. We calculate the derivative of the wave function with respect to 2 parameters, alpha and beta. So these are just the analytical expressions for that. I calculate the quantum force. You have the energy derivative. And this is something which we discussed in previous lectures. And here, what I do is simply to run a calculation first where I find the optimal parameters. So I do first 10,000 Monte Carlo cycles, and then I have a guess for the initial variational parameters. And I let this code run, and now I get a roughly 4 iterations. I find the optimal values. So this is my, the function value. It should be 3 exactly. This is the one which I get before I start the large calculation. So I find the values, the optimal parameters, and then with the optimal parameters, I launch the large Monte Carlo calculation. And you see now that I have this powers with base of 2, so 2 to the 19th. So first I find the parameters with the optimization, and I use Broyden's method, which I would typically recommend, actually the BFGS method. I would typically recommend using one of these methods. And then I run the big machinery. I find my energy, which is pretty good actually. The exact result for this case is 3.0. So even with a wave function which may not be the exact one, you're getting pretty close. I would say this is an example of a system where the Monte Carlo machinery is actually giving us something which is pretty close to the analytical result. And then the resampling tool, there is one here where we do the blocking, and you could then just take, because what I'm doing now is I'm writing to file all the data sets, and you will see in the calculation of the energy, I have a printout statement that I just write the energy as a function of Monte Carlo cycles. So that's my observation, which I then feed into the blocking method. And you can, if you want to, you can just use this function. So it takes the file with just energies. It doesn't have the energy squared. It doesn't need it because it calculates the variance using the blocking method. So it means that in your Monte Carlo machinery, when you estimate the variance, you will do that as a post-analysis. And here you can use the function which was developed by Marius. And I think I should have you can have a link to look at the article which he wrote based on his frustration with the derivations of Friedberg's method. And this is the code which he provides for an efficient calculation. And you can then just load the data set. Let me just do that. And you can load the data set and you have the mean value, and then you have the standard deviation which the method comes up with. And this will be the final numbers which you would publish. Very exciting. Okay. Does it sound pretty clear? So what I put in here is actually an analysis of the autocorrelation properties using NumPy's default pseudo-random number generator. So what you will find here is just a set of runs where we calculate the autocorrelation function. You can look at this autocorrelation time. We calculate the standard deviation, naive method. Then you calculate it with a covariance. So what you will see here is that with this random number generator, which has been tested, widely tested, the stochastic variables are almost independent. So that means that all these methods here, whether you would do the standard covariance, even the naive method, where you just calculate the variance, you calculate x squared, and then subtract x squared minus the mean value squared, you will find that these methods here basically almost give the same result. So this is a case where you now have a pretty good standard random number generator. But if you have a crappy one, then you would probably see big differences here. So you could take these codes if you want to and just play around with them and test the different methods. So in here, there are, so the default random number generator is this one. It's called permuted congruential generator. And it passes all standard statistical tests. Actually, the test which you see here about the covariance is one of the tests it has to pass. There are many more tests, actually. This is an art by itself. So there's a big community out there where people have dedicated most of their life on making random number generators. I like that topic, actually. I think it's fun. So this has periods of 2 to the 128. And it's normally called astronomically long period because it means basically that it's very unlikely that you will make a calculation where you have 2 to the power of 128 Monte Carlo cycles. So you saw the time it took in here where we had 2 to the 19. So using that random number generator assures that the random numbers you generate will be pretty distinct. So I normally recommend using the tested standard default random number generators. And here you can see now this is the correlation function which we discussed. So it's the covariance here. This is actually this, it's called a normalized autocorrelation function. So this is the calculation of the this function which we called f of d, and this is divided by the variance. And so when t is equal to 0, then this is just 1, as we saw in that example. And then in here, instead of using a standard brute force calculation, you can actually perform a fast Fourier transform computed calculation of it. And this is normally what is implemented. We are not going to discuss that here. And then you can calculate the variance of the sample mean. These are the quantities which we have been discussing. And this is the exactly the same functions which we had in the discussion of blocking, where the C of t is the so-called correlation function we defined. And then you can calculate the correlated standard deviation or the mean by this recipe here. And then you know that the naive one is typically sigma divided by square root of n. This is the naive one. And then you can look at the integrated autocorrelation time, which is given by this quantity. So these are the same things which we discussed on the whiteboard before the break. So these are all these elements are just included here. And then there is a bootstrap evaluation. So for the uniform distribution, then you know that the mean value is exactly equal to 0.5, 1/2, and this is the exact standard deviation. So for the you probably know that for the mean. Let me just show you that one. Have you seen the calculation of these quantities for the uniform distribution? Okay, I see that not how you get those numbers. So let me just switch back to the whiteboard. So this is a small digression. So if you think of the uniform distribution, that is a P of x, D of x, which is equal to 1 when you have x between 0 and 1 and 0 else. So if I calculate then the expectation value of x, which we also wrote like this, and we wrote like mu, this is the integral of 0 to 1 of x, of P of x of D of x. And then you see that this is simply 1/2, pretty obvious. And then the variance, sigma squared, is then obviously 0 to 1 of x minus mu squared of P of x of D of x. Then you will find that that one has to be 1 divided by 12, which means that the standard deviation, which is the square root of that one, is 1 divided by square root of 12. So this is something which you can do analytically by paper and pencil very easily. Okay. So let's go back. So just a quick reminder of those results. Let me find, there we are. So these are basically the quantities we want to set up. And then we generate with a random number. So this is in this case, I do 50,000 numbers. I set the same seed because I want the same, be able to repeat the calculations. And this takes the default RNG here, which is this with astronomically long periods. That one, so this is number of points, min and max, the values. The mean value is not exactly 0.5 because I have a limited number of variables. So if I were to increase this one, say to 1 million, then this would get closer and closer to 0.5. And one of the things you will typically see if you count the number of measurements which you have in boxes, let's say from 0.1, 0.2, etc. So just to give you a feedback of a feeling of that one, let's just go back to the Jupyter notebook. So if you take the uniform distribution and you simply make a histogram from 0 to 1 with boxes which go from 0, 1, 0, 2, and all the way up to 0, 9, and 1. And then ideally now, if you have a total number of 10,000, what you should see is that in every domain here, there should be 1,000 measurements. But you will normally don't see a perfect distribution. So you may actually get something which, if this is 1,000 now, you may actually get something which perhaps looks like this in the next one. The next one may be smaller, a little bit larger, then closer, etc. And then perhaps the last one looks like this. So you don't get a uniform distribution. But if you increase the number of data points, you will get something which looks closer and closer to a uniform distribution. So with few data points, you will get some histograms which are not exactly equal to the number of points divided by 10. Okay? So that's also one of the useful tests of a uniform random number generator. So actually looking at the distribution of numbers is also one of the tests which you want the random number generator to pass. So let's do that and go back again. So this is roughly what we just calculate the sample mean and the sample standard deviation. So it should be actually 1 over square root of 12, which is this one, and you see that you don't get exactly that one. Then you can make plots here, you can calculate the, you can see the convergence of the samples. And in this case here, you can also calculate the autocorrelation function. So if we do that, and we plot, you can now see that the first value is 1, as it should be. Now, if you go to the next one, in the autocorrelation function, you will actually have 0, but you're not getting exactly 0. And there, what you want to calculate then is also look at the max value when t is larger or equal than 1. So remember now that what we tested previously in that example code, which we run before the break, you saw that the autocorrelation function was 1 when t was equal to 0, which you get. And then you want these values to drop quickly to 0. And you see now that they're actually getting smaller if you take the absolute value. And then after some time, they just disappear. So if you plot the autocorrelation function, you will see something like this. So you have 1 here, and then you will see these very, very small variables here. And if you plot this on a log scale, you will see now that it's getting smaller and smaller, but it is not exactly equal to 0. So these are typical tests which you would then have for the autocorrelation function. Then you can calculate this autocorrelation time, which is a very useful measure. So actually, many people, so there's a reason why you don't calculate this one in your Monte Carlo calculations, because it's time consuming. But if you can do it, it's very instructive to actually calculate this autocorrelation time. And this is a quantity which we discussed before the break. And that gives you a kind of measure of how many Monte Carlo cycles you need effectively before your stochastic variables become independent of each other. So when this quantity here drops to 0, then that is a kind of measure for you having reached this stochastic independence. However, as I said, this is expensive to calculate. So this is roughly, so if it's uncorrelated, it should be 1/2. And roughly here we need something, so this is the effective number of samples which we need before we can view this as uncorrelated. And in this case, it's pretty large. So you can visualize that one. And yeah, this is not so interesting. Then you can calculate the standard deviation in a naive method. And this is actually the quantity which you would typically set up. And in this case here, it's actually pretty close to the exact result. And then you have the covariance method, where we actually use the covariance, which we discussed. So essentially everything we had before the break in equations on the whiteboard are actually implemented as codes in here. So I just invite you to take a look at the codes, and then you can look at the integration time, the naive sigma, and then the corrected sigma, which you should get. And then the ideal one is actually the one which is 1 over square root of 12 here. And this just continues, not too exciting. Then you can use the bootstrap method. And you can now see if you use the bootstrap, and this is with the mu, which is centered there, you can then see how the numbers actually distribute. So you started with a uniform distribution. And with the bootstrap, when you run a series of bootstrap experiments, so these are the bootstrap results, you see now that you're getting a variance of standard deviation, which is pretty close to the one you want. And the mean value is centered around 0.5. And this simply counts the number of times you measure the mean value, and according to the different bootstrap experiments. So in this case, we have run, I have to remind myself how many bootstrap experiments we run. I think I run as many bootstrap experiments as, no, I did 3,000 bootstrap experiments. So what it does, it simply converges towards the central limit distribution result. And you will see now that the calculations of the mean value, so this is actually the different values for the mean value as a histogram. And these are centered around the mean value here. But it shows you the distribution of mean values of 3,000 bootstrap experiments. And you see that this moves towards a Gaussian. So this is the central limit being applied. Nothing but that. And then you can use the blocking method. And then I actually collected everything here. So if you lose the blocking method, this shows you the kind of plateau which you're actually looking after. And if you compare all these methods with different number of values, you can now see the naive one, the covariance one, the correlation one. You have the naive one, and then you have the exact one, which is listed here for that number of measurements which you have. And then you have the bootstrap result and the blocking result. And you'll see that the blocking is actually the one which brings us pretty close to the exact result here. Okay, so I'm going to stop here. Take a look at these codes if you want to. This is just an implementation of all these different ways of calculating the standard deviation. And you can see now that with the naive result, this is, it obviously gets, it has its limits. For this random number generator, you're actually getting something which is not so far away from the exact result, because the random number generator is pretty good. But for your Monte Carlo results, you will most likely see a larger deviation between the naive result and the final standard deviation. Will we stop here? Oh, by the way, we can discuss the one-body densities in the lab session, if that's okay. Any questions? Okay, so I'm going to stop here.